All right, today we're going to do a demo. We'll start with this is take 2. And remember last time in class we did the jump table, the switch statement, which is implemented with the jump table. And so here's our guess jump table. And notice that these values are the addresses of the first byte of the code for each one of those individual cases. So let's go ahead and start the debugger here. We're on batch input output. We put a 2 there. And so let's single step through and see what our trace tells us. So here we do sub SP 2, so that allocates storage for the guest. Stros is pick a number. Now when we do deci, we're going to do decimal input from the batch. So guess gets 2. Now check this out. We load the index register with guess using stack relative addressing, right? So let's see what happened. What is in the index register? Check it out. 2. And why is that? That's because guess is 2, right? And now when we do ASL X, what's going to happen? It's going to become 4. Are you with me? Mm-hmm. And now we're going to branch to the guess jump table using indexed addressing, but that X is 4. So this is at address 0, 1, 2, 3, 4. So the 0027 is going to get added, or it's mem sub 0027, which is where we're going to go. Is that right? So let's see if it happens. Boom, 0027, we jump straight to case 2. And so it's going to print right on, and then character output the new line and stop. Okay, so there's the demo of how the switch statement works. We started with a little demo with the switch statement, and then the second example that we did at the end of class last time was dynamically allocated variables, right? Variables of type pointer, where you use new to allocate storage from the heap. And to remember what the protocol was for new, what's the precondition? No, the precondition is not the index.
You loaded how many bytes?
How many bytes you want to allocate into which register?
The accumulator.
Into the accumulator. Then you call new, and then at the end of new, what does new do? It puts what?
A pointer to the allocated bytes in the index register.
Yes, it gives you the pointer to the allocated bytes in the index register, so that you access the index register that way. All right, and we went through this code for, this is the example that we did, that we went through the code for, we did new A, and then star A gets 5, and so on. But now what let's do now is let's take a look at the actual code for new. Now this is actually pretty slick, I think. So here is a second slide of the middle part of the program, and it goes up to location 0064, and then check this out. At the bottom of the program we have this code, which is operator new. Now you guys, this is pretty neat. Look at this. It really only takes 3 instructions to do it. Check this out. Here it is on this slide, on figure 6.41, the last part of the slide. But look what it does. So new is a symbol, right? That's the first, it's the address of the first line of code in the new subroutine. And notice here we've documented it. Precondition A contains a number of bytes, postcondition X contains a pointer to the bytes. Now, let's take a look at the symbols that are defined. What do we have down there at location 0074?
Heap pointer.
Yeah, that's the heap pointer. And what is its and what is the value at heap pointer? What is the it's a dot .addRSS, right? Mm-hmm. Mm-hmm. And what is the address of heap? But what is heap? Heap is at location 0076. So the 0076 is the code that's generated by the .address command. Are you with me? Now, does everybody see how that worked? I mean, how that gets set up? So what this is doing is this is setting up the heap starting at address 0076, right at the bottom of the program. And every time you call new, what it does is it allocates storage, one more section down in the code. You see how how that picture works? So in our memory map, well, if the program is here, this is the app. We said that the heap grows down this way. So this is the heap. So here it is. Here is the picture. Here's the code that actually has the heap growing down this way. It allocates storage one more down, one more down, one more down. So now look at this. Look at how neat this is. What's the first line of operator new? Load the index register. What? Heap pointer direct. All right. So what does that get? The very first time we call new, what gets in the index register?
The address.
What value? 0076. And then you add accumulator, heap pointer direct. Now what was in the accumulator? What do we assume was in the accumulator?
How many?
How many bytes? So if we allocate 2 bytes, now what's in the accumulator?
The next.
00, what value?
0077.
No, well, no, because we allocated 2 bytes for we allocated 2 bytes for the integer, right? So that'd be 0078. And now what happens? Store accumulator what? Heap pointer. So now at heap pointer no longer has 0076 in it. Now what does heap pointer have in it? 0078. So now the new heap pointer is pointing to the start of the next place where it's going to be allocated. Are you with me? And furthermore, what's the post condition? X contains the what? The pointer to the byte. So what will X contain? What does X contain?
Address.
Yeah, and which address does it contain?
The one of the.
What value?
0078?
No. 0076.
Because we loaded it first.
But I thought that we incremented it.
Yeah, in this particular, this is a slightly different from the stack. With this, what we're doing is the heap pointer is pointing to the one that's going to be the first byte that's being allocated.
Oh.
And then it's being incremented so that the next time it will point down to, it's incremented by the correct number of bytes so that the next time it will be pointing to the next one and they won't collide, because you've allocated that many bytes. So it's really, look at this, only 3 instructions and there's no stack, there's no on the run ret val or parameters.
So return 0.
Yeah, ret 0, there's no local variables.
Oh, so that it acts like a function call?
Yeah, because we say call new.
Okay.
And this is ret 0. So it is a subroutine call, but it uses a different protocol from what we normally use for the for standard, void and non-void functions in C++.
How does the
methods.
How does it work with the dot end right there?
Yeah, that's the end of the program.
Right.
And the heap manager is at the bottom of the program. Is at the bottom of your program so that the heap will grow this way.
So it can just.
So it's all part. You have to include this code in the program.
Right. So because you said, like, for example, when you update the heap pointer, it'd be 0078.
Yeah. So the next time somebody calls, the second time when we said new B, when we translated new B,
Right.
then B is going to be at 0078. A will be at 00.
So this is the dot end. The sentinel is never reached unless it goes past that.
No, hold on.
Understand how?
Dot end is the sentinel for the assembler.
Right.
The assembler assembles the whole thing, your translated program and subroutine new.
Right. But it.
And it generates that code as, just like usual. See, here's the previous, it's right next to this. It's at the bottom of the program. Here's the previous slide, so it's right next to that.
Right.
So dot in, you have to compile the heap, in this simple system, you have to compile the heap manager along with, at the end, at the bottom of your program, along with your program.
Okay, so since it's dynamically allocated, the information can be past the dot end, past the sentinel.
Oh, sure. Oh, yeah, that's a good observation. A good observation is that the allocation happens during the execution of the program. And you know, you can,
The assembler doesn't need to assemble anything past
no,
the dot end, right?
because that memory is there for you to use.
And you can access it.
And you can access it. This is just
Just
the
like-
sentinel for the assembler, yeah. You know, in the very beginning, when we looked at the memory dump, you know, that memory is all there. You can go, you know, do stuff all over memory anywhere you want. Yeah, but that's interesting that, yeah, that this is dynamically allocated during runtime. It's not statically allocated like globals are. Okay, so now let's do a demo of, because the tracer actually can trace even the heap. So watch this. All right, so this is figure 641. Okay, so now we're going to demo program 6.41, the program in figure 6.41. So here it is, and we'll copy, and oh, here, let's scroll down. See, there's operator new, there's that we just looked at. So we'll copy to source. We will compile it. Assembly is successful. And I guess there's no input here, right? Everything is A gets 5, everything's immediate. All right, so let's go ahead and do the, start the debugger. Now check this out. This is really slick. So we'll single step. First thing, we branch to main, and here's our main. And now watch what happens when we do A gets new int. Well, first we load accumulator 2, so over here the accumulator gets 2. Are you with me? Now we're going to call new, and notice here it's pound A. So now watch what happens when we call new. Boom. There it is. There's the heap labeled with A. So here's the global variables at a fixed location. Here's the stack that has the return address, and here's the heap. Is that slick or is that slick? Okay, and then we add accumulator heap pointer. So the accumulator, we're about to execute add accumulator. Okay, so now here's the 78, right? Remember we said 2 plus 0076 is 0078, and then we store that into heap pointer. So now if we go back to the memory dump and look at that location in memory, it won't be 76 anymore, it'll be 78. Okay, and so we continue to single step through this. Okay, and now we do star A gets 5. So A is 0076. Okay, because that's the value of the pointer. And then here at 0076, there's the 0. And now, check this out. We store accumulator A using indexed addressing. And what's going to happen? 5, boom, on the heap. Is that cool? Okay, and now we're going to call new again, right? So we're going to call new, and there's the B. Are you with me? Okay, and then we're tracing through the new, and then add A, and then store A, and then ret 0. And now we're going to do star B gets 3. So, and notice that B is at 0078, right? The value of B is 0078, and 0078, that's where B is. And are you with me? On the heap, yeah? And then, boom, there's the 3, okay? And now we're doing A gets B. So now what do we say A gets B? What's going to happen when we do A gets B? Yeah, so these this 76 will change to 78, right? We hope. Okay, so boom, 76, boom. So there's a 78, right? And now we're doing star A gets 2 plus star C. So first we load accumulator of 2, so there's the 2, and we're about to do add accumulator C. But now what is C pointing to? The same thing, what? Oh no, not the same thing. C is pointing to A, right? What I used to point to, and so we add that, and so there's the 7, and then boom, there's a 7. Okay, and then star A equals 7, star B equals 7, star C equals 5. Yeah. All right. Okay, so that was the demo, and here's figure 6.42 that shows the figure from the book that is like what we saw on the demo. So now, did you have a question?
Yeah, the sentinel in PEP8 is at address 77.
Yeah, it actually no code gets generated.
No.
Dot .end is the sentinel for the assembler.
Okay, and so there's nothing at 77 as far as it's concerned that is.
Well, there is going to be something there.
It's the
But
second
it's-
half of the first integer. It's the first.
Well, actually, that's going to be the address of the, yeah, that's going to be the address of the of where the first integer gets allocated.
Maybe the second half of it.
Yeah,
Okay.
yeah.
Yeah, that's all I was wondering. That's perfect.
Yeah, that's going to be there when you run the program, yeah. All right? Is everybody good? Now, local pointers, I don't think we need to spend too much time on local pointers because the only difference is, well, let's spend just a tad. The only difference between a local pointer and a global pointer is that the local pointers are allocated on the runtime stack. So actually, let's do this. Let's start it. So the recipe is you allocate storage for the pointer with the sub SP and deallocate with add SP. And now, but here's the thing. How do you access, we already have an addressing mode for this. How do you access the cell to which the pointer is pointing? Well, we already have the addressing mode for that. If the local variable is like an integer, you would access it with stack relative, S, right? But now because it's a pointer, you just allocate it with, you just access it with what? Stack relative deferred, which means it's the memory of where you go to access it. So we already have the addressing mode for that. Is that neat? See how all of this stuff works? All nicely together? So look, here's the same program. Let's start it. Let's just do the first little few lines of code here. Okay, now what's our here's going to be the runtime stack, and what variables do we have on the runtime stack? A, B, and C. Are you with me? So here's A, B, and C. Yeah? And this is the stack frame. So first we'll branch to main. Now, how are we going to define A? It's a local variable. So when the stack pointer is here, what's going to be the offset from the stack pointer? 4. So here we have A, and what do we put here? Dot equate is right. And then B, dot equate 2, and C, dot equate 0 is right. Yeah? And then here is main. Okay, and now what's the first thing that main, and we'll just do this few lines here. So now how do we do A gets, oh, you're right, we have to sub SP, don't we? Sub SP, how many bytes? 6 addressing? Immediate. And what are we allocating here? In what order do we have to put them? We got to put A, B, and C, right? A, B, C. And then, and now how do we do A gets new int? Load accumulator. Load accumulator to immediate, and then call new. And when we call new,
Is it pound A?
it's pound A. And now, aha, but now there's the question. Wait a minute. Yeah, this is the question. Where do we want to store it? We want to store accumulator because where do we want to store it?
A.
We want to store accumulator at variable A, but now using what?
No?
SF?
SF?
Oh, is it S or is it SF? Good question.
Just S?
What do you think? What do you? Yeah, yeah. Ooh, this is a really good hard thinking question.
We're storing the.
We're storing the address, so we want.
The index register has the
That should be store
I
X.
forget what deferred means.
Yeah, it could be store X.
deferred means mem sub.
Oh, then we want S, I think. Because we want to store, because we're getting the address and we want to store it right at that.
You want to
spot.
store that address here.
Yeah.
Is that the pointer? Then
Yeah.
store stack relative. S.
Yeah.
Yeah, S as and not SF.
Right.
That's isn't it an X? You're storing that.
No, because the pointer is in.
Oh, you're right.
Yeah,
Not store accumulator. The index register is what has it.
Pointer.
Isn't it right?
Yeah.
Yes. Oh, good call. Yeah, that pointer is in the index register, but that pointer is what that value of that pointer is what has to go in
That'll
here.
put the address there, right? That'll put the address of the pointer into the.
No, it will put the pointer. Well, a pointer is an address. Yeah.
It'll put the pointer right at.
Yeah, yeah. It will put the address. It will put the. It will put the address of the cell that A points to in there.
Yeah.
I think I said that right.
Okay.
Maybe we should do one more line.
Well, let's.
Now let's do star. Yeah, let's do one more line because now let's do star A gets 5. So now how do we do star A gets 5? Well, something's going to get 5. So the first thing is what? Load accumulator, 5, immediate, then what?
Store accumulator.
Store accumulator, A,
That's SF.
S,
F.
F,
Boom.
dot, dot, dot. Are we good?
No.
Let's see. Here it is. Check it out. Did we do it right? Check out especially this and this.
That's good.
Yep.
Are we good? We're so good.
We're so good.
So here's a picture of it. Figure 6.44. A is the picture as we visualized it in HOL 6 level. And B is what it is with the actual hexadecimal values for the addresses that are in A, B, and C. Are we good? Okay, so now we just have to do one more thing. And then we will be done. And that is, all right, are you ready for this? Do you remember in data structures when we did linked lists?
Yes.
Ooh.
I think it makes so much more sense now.
Good,
Okay.
good.
Global structure. Oh, struct.
Yeah, so, and remember, whenever we did a linked list, what did we have to do? You know, we had a node that was like this, and then this pointer pointed to the next one, right? And so here we had, this one was data, and this one was like next. We called this one data and this one next. So what is this collection of variables with different types? What is that called? It could either be a class, and each one of these could be what? Attributes, or it could be a struct. Okay, a struct and a class are actually the same thing. In fact, do you remember, we actually did this in data structures. Do you remember the difference between a struct and a class? In fact, a struct is a class. In C, they had struct. They didn't have class. In C++, they added object-oriented programming to it. And what they did is they used the struct for a class.
Does it not have polymorphic dispatch?
No, that's not the difference. But that was a nice try. It has something to do with the default access.
Private versus public?
Yes.
Structs are automatically public.
Yeah, now I have to remember which is which. The only difference is if you don't say public or private and you have a struct, it's automatically public, I think. I should have looked this up before I came to class.
That would be my guess. Like,
And if it's a class,
The class will automatically be
the default is private. I believe that is correct. I believe that is correct.
oh really?
You would have thought the opposite? You know, we always, I always put, when we do a class, I always put either public or private, so I never have to worry about the default, and so I always forget which one it is. Are we gonna let Kyle be our Google lookup? Default access for struct. Or default access for class.
Private by default.
Private by default is struct. Oh, it was the opposite. Oh, I'm glad we have you here because I would have recorded it wrong for posterity.
Oh, that's C sharp. Hold on.
Oh, that's C sharp. Oh.
I already wrote private. You can
Me
have
too.
it. Sir.
Structure and class are the same except default access
Oh.
for structure are public. There you go.
Ah, so I was right.
You're right.
I was right.
C++.
Oh, so that's interesting. C sharp was different.
Yeah.
Whoa. Why? Now, why did they do that? Tell me, why did they do that? That's so confusing.
The other person was thinking like me.
Okay, at any rate, here's how we access global structures. So in order to have a linked list, we have to be able to access structures. So this next example shows how to do struct, how to translate structs. So what you do is you equate each field of the struct to its offset from the first byte of the struct. So here's an example. Let me just make up sort of like a generic example. Okay, so here's a struct, and say that these have 4 completely different data types, right? Mm-hmm. Then the way you do it is, it's kind of like we did it with the offset from the top of the stack. Only what it is here's the address of the first byte, and then what you do is each one of these, you see, each one of these. You have the offset here. You have the offset from the first byte of the struct. So here's kind of like a picture, a diagram of the concept. You see? So whenever you name, each one of these fields has a name, and what do you equate that name to?
Offset.
You equate that name to the offset from the first one. Are you with me? You equate that name to the offset from the first one. And when you allocate this, how do you allocate storage for this? If it's global, you allocate it where? In a fixed location in memory. With what? Dot block. And then the way you access a field, you load the field into the index register with immediate addressing, followed by an instruction with indexed addressing. So you use indexed addressing, but instead of the index register being, which one in the array, it's the offset like this. So this is kind of like an array with variable. It's kind of like an array with variable cell widths, cell sizes, but each one has a name. And then the offset. Yeah, does that make sense? So this is if you get that idea, this is the picture that does it. So here's the program. It's struct person. Now let's think about how person is done, how this struct looks. So this was one in general. So now what does our person struct look like? Okay, first of all, it's char first. So here's our struct. Okay, and this one is called char. Okay, so there's going to be a character in here. Now, what's the second one?
Last.
Last, and it's another what? Char. Okay, so this is another char. So this one is first, and this one is last. Okay, and then what's the next one? Age, but age is an int, so that's how many bytes? That's 2 bytes. So this is an int, and the name of this is age. Are you with me? And then what's the last one? Gender, and it's a char. So that's a short one again. So this one is char. And that's, is this gender? Are you with me? So now look, what are the offsets? So now, can we predict what the offsets are going to be? So here's the first part of the record. Here's the first part of the struct. Yeah. So now, what will it be? How will we define first? So first will be what? Colon what?
Dot equate 0?
Yes. Dot equate 0. Does everybody see that? Dot equate 0. And then last will be what?
Dot equate 1?
Dot equate 1. And then age will be what?
Dot equate 2.
Yes. Dot equate 2. But now gender will be dot equate what? 4, because age takes 2 bytes, right? So gender will be dot equate 4, right? And now we have person of type oh, and by the way, that says struct, right? So whenever you declare a struct in C++, no storage gets allocated. That's defining a new type. Are you with me? Or defining a new class. But now what about Bill? How do we allocate Bill? How do we allocate Bill over here? Huh? So is Bill global? Yes or no?
Yes.
Bill is global. So how do you allocate globals? Dot block. But but now what do you put in the dot block?
The total number of bytes you need.
And what is that? That is correct. The total number of bytes that you need. And how many bytes do we need for Bill?
5.
5. So what do we put here?
5.
5. Now what about the tag? Oh. Now we have to put tags here. Okay? We've got to put tags here. So the tags we're going to put here are pound. How do we want to display first? Oh, have we done a character before? I don't think we have. Do you know what it's going to be? It's going to be a pound 1C. So this is a pound 1C, and this will be what?
Pound 1C.
Pound 1C.
Pound 2H or pound 2D.
Pound 2D.
And a pound 1C.
And a pound 1C. And now, what do we put here? What are we allocating here for Bill, dot block 5? What do we have to put?
Global.
Well, I know, but what we do is so that it will let we put first, last, age, gender. Okay. Are you with me? So, pound first, pound last, pound age, pound gender. Okay, and what will the debugger be able to do? It will be able to add up. It will come to here and see that this is 1C, 1C, 2D, and 1C, and it will add these all up, and they had better equal 5. Are you with me? Mm-hmm. And then what happens when we do cin? Now, how do we cin Bill dot first? Let's just do the one. Let's just translate that one line. Cin Bill dot first. So what happens there? Cin Bill dot first. So it's carry. Oh, but before we do carry, yeah, it's carry what? Bill, but the question is, we kind of jumped ahead. It's Bill, but what addressing mode? Indexed address. So if we're going to use indexed addressing, we better have done something else first, right?
So you have to
It's what?
load
No, it's load X. No.
first.
First.
Stack over. I guess it would be.
Because don't you want
Ooh, good question.
It would be immediate.
It would be immediate.
That makes sense.
Okay, so let's see if we did it right. Did we do it right? And et cetera. I'll let you guys do the et cetera. Okay? And now, there's only one more step away from this. Now that we see how to do a struct, now the question is, and then here's some pictures, okay, with bill.first, bill.last, bill.age, bill.gender, and I'll let you read through that. And now how do we do a linked list? Ha-ha! This is so way cool. We are moving through this kind of quickly, but I think it sounds like you guys got the concept, and so I think you can deal with this pretty well. Linked data structure with a local pointer. So, actually, before we look at that recipe, let's take a look at the program. What we have here is struct node, int data, node star next. Look familiar?
Yeah.
Look way familiar? So, but here it is. Look, it's a struct, right? Okay, so here's an int, and this is called data. And here is an int, actually this is a pointer, right?
To the next one.
And that's called next. So what do we equate data? So what's our data in our next? Data is going to do what? Data is going to what? Dot equate 0. And next is going to do what? Dot equate 2. Gesundheit. Are you with me? Okay, and now what variables do we have? Node, star first, and star p. So what is our stack going to look like? Our local stack of local variables? So here is,
First.
is this going to be, what order do we get them in?
First and then
First, so this is first,
first is first.
and P is here,
And those will be addresses.
and value is here. So are there 3 of them? And so if our SP is here, after we do the allocation, what will they equate to? First we'll what? Dot equate to what?
4?
Yes. Dot equate to 4. P will do what? Dot equate to 2. And value will dot equate to 0. Right? And then, when now let's do a few lines of code.
So we have to sub SP.
So we have to sub SP. So here's main. So we will sub SP how much?
6.
Sub SP 6 immediate, and you can worry about the trace tags on your own.
So then we need a
And now we do first gets 0, or first is just an int, is that right?
oh.
Yeah.
Is first an int?
No, first is a pointer.
Yeah, first is a pointer.
First is a pointer.
With the low.
But no, but still it gets 0. And it's a local. Yeah, here let's do first gets 0. So load accumulator what?
0.
0 immediate. Store accumulator what?
First.
First addressing?
S.
No, it's a local variable.
SF.
First
S.
S or SF?
Oh, no.
Isn't it S?
It's just S.
It is S.
It's just S. That's null.
I was thinking you were setting the.
That's null. 0 is null.
I'm following.
Are we good? And now what's the next one?
Same value.
C in value, so that's what? Deci,
Jesse.
Value.
value addressing, S. And now what?
Wow.
While, okay, let's skip the while, because we're running out of time. And let's do this interesting one. P gets first,
Okay.
Okay, so load accumulator.
load accumulator,
First.
first, addressing,
Stack relative.
stack relative,
Store accumulator.
store accumulator,
P.
P,
Stack row.
stack relative. Now, are we going to do a new?
Yep.
First gets new node. Load accumulator what? No?
Wait.
How do we know?
How do we know?
Well, a node.
Isn't it 4?
4.
Because then node is.
Why is that? Because a node has 4 bytes.
Yeah.
Are you with? And then, are you with me?
Yeah.
So here's our protocol for calling new. So we put the number of bytes in the accumulator. Then what?
Call new.
Call new. And now
Because it's
Store.
and now the index register has that pointer that got returned. So what do we do?
Store into first.
Store it into, okay, so store index register into first using what?
Stack relative.
Stack relative, is that right?
Stored in the first. Yeah.
And now, how do we do? First arrow data gets value. Well,
we have to load the.
load accumulator what? This is, we'll end with this. Load accumulator value,
Stack
okay, as addressing?
Stack relative.
Yeah, okay, stack relative, you say. Okay, but now what? Now what? Oh my goodness, what are we storing it
We
into?
need to go to the first part.
What are we storing it into?
The most
For-
significant byte of where.
We're doing first arrow data. So we want to store accumulator into first, but how do we do this arrow data?
Index.
Yeah, we load index register with what?
With data.
With data, yes.
Data.
With data.
Yeah,
Stack index.
I think so. No.
Data equated to 0.
Don't you want it? Don't you want that?
Yeah, that's what.
No.
We do want data to be 0.
It's immediate.
Yeah,
Yes.
yeah,
Yeah.
good call.
Yeah.
Oh, sorry, I didn't hear you. I'm hard of hearing. I keep saying. Okay, and now what?
Now we.
Load or store.
No,
Store accumulator.
store accumulator.
First. Stack index.
Stack.
First. But now what is first? It's a pointer, right? Oh, man. But we have something in the index register, but first is a pointer.
So is it
X.
SX?
I think it's SX.
What's the other one?
It could be SF.
SXF.
Is it SX or SF or SFSXF?
It's not because it's deferred, because if you're just adding it to the address, it'll stick it there. You need to add it to what first is pointing to.
It needs to go to the stack
So it
first.
just needs to be deferred.
So you're saying SXF.
Yeah,
Is that what you're saying?
yeah.
Let's see. Drum roll.
Yay!
Wow.
Did you win?
Yeah.
And yeah, S was right back there. Don't know why you doubted us.
No.
I was just trying to keep you on your toes. All right, you guys.
Why is it SSX? XXF?
Because it needs to be deferred. Because if we were just adding it to first, first has an address in it.
Makes sense.
So we need to go to the location mode first.
We need to, I understand why it needs to be, I don't know why it needs to be deferred. I understand the SX part.
You know, maybe the thing to do, we're out of time now, sorry, but maybe what would be interesting to do, maybe we'll do this at the start of class next time, would be to run figure 6.47 through the debugger on your app.
There you go.
And I think you can see, you can actually see what's in the index register,
Okay.
and then you can calculate what happens here. Well, this is about as involved as it gets. And you can actually, this program actually constructs a linked list. And your homework assignment is to modify this program. So you go to this program, you copy to source, and then you stick in some extra code to do a little manipulation. And then you'll use these little address emails. But most of the program's written for you, so it's pretty short. Oh, I've got homework to hand back too. Anyway, so see you next time.